Hello, hello, hello. Hi, good evening. Welcome to this problem solving session on modeling and simulation of dynamic systems. So, my name is Parth Joshi. So, I'll be conducting this session for today. Uh, I'm just waiting for a couple of more people to join, and then we can start in like 2-3 minutes or so. Hello, good evening, sir.
Hello.
Yeah, I think no one else has joined the session yet. So I think we can start. Yeah, so I think we can start the session. So I'll just give a brief introduction about myself. So my name is Parth Joshi, and I'm pursuing my PhD at IIT Bombay in the Department of Mechanical Engineering. And I have been conducting these weekly problem solving sessions for this course on modeling and simulation of dynamic systems. So like I'm basically a recipient of the Prime Minister's Research Fellowship for my PhD research, and as a part of this fellowship, I got this opportunity to interact with all of you for this problem solving session. So this was like a brief introduction about myself. Uh, so sir, have you have you joined the earlier solving sessions that were conducted?
आवाज हेलो सर नॉइस आवाज बहुत कम आ रहा है वॉइस इज वेरी
Are you not able to hear me?
माइक पे सी इट इज ऑन द आई एम ऑन द मीट बेसिकली गूगल मीट आई हैव
Sorry.
कनेक्टेड दिस
Yeah. So are you not able to hear me?
इट इज कमिंग ऑन द मोबाइल बट इट इज नॉट दैट मच लाउड
Oh, I see.
चेक एक मिनट
Okay. So like better now? Any better now? Are you able to hear whatever I'm saying?
आई कैन सी दिस बट द वॉइस वॉइस इज वेरी लो सर आई हैव मेड फुल वॉल्यूम ओवर हियर
Oh,
आई कुड नॉट अंडरस्टैंड
so if possible, sir, like can you join from your computer? Like if it is possible, I think that may be better. Are you able to hear me?
यस यू कैन टॉक सर नो
Is it better now? So are you able to hear me?
हेलो
Hello? Yeah.
Yes, yes, yes. I'm hearing it.
Are you able
Okay,
to hear me now,
just
sir?
hello.
Yeah, I can hear you clearly. So like start the session? Are you able to hear me
One minute.
clearly? So are you able to hear me?
Yes, yes. You can speak, sir.
Yeah, sure. Okay. Yeah, so can you just tell me, sir, like where are you from, like and like just can you just tell me, sir, have you like gone through the videos of the earlier problem solving sessions for and do you have any feedback on that or any questions, comments on that?
Sir, I have not gone through this bond graph. Basically, this is first time I am learning this bond graph.
Okay.
So unable to attend that session. Basically,
Okay, so actually second week's session like was on that like part bond graph modeling. So
yes,
like
yes.
if you have any specific questions, like we can take those on like bond graph. It's basically just like a graphical technique of like representing the system model. So yeah.
Mhm. See, basically the The conventional dynamic, see, the modeling of the systems I know, but the bond graph they have some different conventions over there, no?
Yes,
So
yes, yes.
that is somewhat not. See, once I have to try it, but basically, so the basic thing I understand over there. Somewhat I understand over there, but still I'm unable to grasp the other things.
Okay. Yeah, I think so. It's like basically there are some like basic elements which are used like for example the basic elements like source
Uh-huh.
effort and source flow, and
Uh-huh.
then the other elements like resistance, inductance and capacitance, like
Uh-huh.
and other elements like transformer and gyrator. So these are the like the basic elements.
Mhm.
And so like for example hydraulic resistance can be again represented by that resistance element. Then we can represent electrical resistance by that same element. And also let us say damping in a mechanical system, that also we can represent using that same element. So it's basically like a unified representation of all these multiple quantities or anything as such. So by
Mhm.
bond graph, basically what we represent is like the flow of energy or flow of power across that
Mhm.
system.
Mhm.
So like so when like let us say in a let us say in an electrical circuit, if we have like a voltage source or current source, so then so when we represent a voltage source, we will represent it as source effort, because voltage
Mhm.
is considered as an effort quantity,
Mhm.
and current is considered as a flow quantity. So like
Mhm.
basically there are like so in a bond there are like both like effort as well as flow, like both these things are involved. So uh, and the direction of that bond basically will in some sense like indicate the direction of the power flow. So like
Mhm.
so whenever there is a source element, so the bond is directed away from that. So so that means that power is actually flowing out of that. And in case of like resistance, inductance or capacitance elements or whatever, the like they are consuming power or storing,
Mhm.
like either they are storing energy or dissipating
Mhm.
power,
Mhm.
like that. So um so that's what like I can say like at a very basic level. And then similarly like spring or basically the stiffness property or
Mhm.
the capacitance,
Mhm.
electrical capacitance or hydraulic capacitance. So they can be represented by the capacitance element. And the mass or inertia, moment of inertia are like that property. And inductance, that can also be represented like by the inertance or inductance, whatever element that is called.
Mhm.
And then we have like the transformer element, where basically we can like kind of where let us say there is a gear ratio involved. So like a
Mhm.
gearbox is kind of a transformer element. So where we uh, let us say either reduce speed or increase speed. And
Mhm.
if we are reducing speed, then we are multiplying the torque. Or other way, like
Mhm.
if we are increasing the speed, then we will proportionately reduce the torque. So that is the
Mhm.
transformer element.
Mhm.
So and the gyrator element is something where so flow is converted to effort or effort is converted to flow basically. So a motor, let us say an electric motor converts like there is a certain supply voltage that we provide, and then outcome is let us say the speed. So the
Mm-hmm.
voltage is controlled, motor voltage is controlled, and we get the output as the speed, let us say, or in case of a generator, we
Mm-hmm.
provide, let us say, the mechanical energy as an input, and the output is what like the potential difference
Mm-hmm.
across that. So basically that so gyrator can be either electric motor or generator or like that kind of an element.
Mm-hmm.
So broadly these are the elements, and then there are some rules, like there are like junctions in a bond. So whenever we are looking at power transfer across elements which are like um, so like common speed, so common speed junction is called as like one junction, or common velocity or common speed, that is called one junction, and the common voltage or
Mm-hmm.
common effort junction, that is
Mm-hmm.
called as the zero junction. So
Mm-hmm.
those are like ways to represent that basically that kind of a power flow. So let us say when we are looking at uh, resistors, let us say resistors are connected in uh, parallel, so then
Mm-hmm.
the voltage across them is same,
Mm-hmm.
and the current is being distributed across the two resistors, let us say. So then uh, the flow is getting distributed, but the voltage difference, like voltage is same. So then that
Mm-hmm.
we can represent it as a zero junction, which is common effort.
Mm-hmm.
And so in other words, like if we have resistors in series, let us say, so
Mm-hmm.
then the current flowing through both these resistors will be the same, but the voltage drop across them will be different. So uh, so then that can be represented as a one junction. So the uh, voltage drop will get added, and the current flow is common. So the common flow, it's a common flow junction. So we can represent that like as a one junction. Like so that's the general idea about the basic. And then another aspect of bond graph is like causality. So for causality, it's basically uh, we can say that it is on, like let us say in the bond, on it's on the direction on which at which we are calculating the flow. So for a source of effort, so effort is known, so known effort is being provided, and the resulting flow is calculated. So that's why the causality, we indicate it on the right hand side for the source effort, and for the source flow it's the other way, like the flow is known and the effort is being calculated. So the for the source of flow, the causality will be on the left hand side of the bond. So like these kind of things, so it's a little bit abstract and maybe slightly difficult to understand initially, but I think if one can practice that, I think one can, I think, get used to it uh, easily. So
Mm-hmm.
yeah, so does that help a little bit?
Yes, yes, yes.
Okay. So, sir, are you like a faculty member somewhere in a college or
Yes,
university?
yes, yes. I'm a faculty member in the college.
Okay, sir. So,
So I'm from Department of Mechanical Engineering,
okay,
and I used to take the subject of this mechatronics.
I see.
So, uh, so in that basically I required the some of the things I also taught.
Okay,
But we have the simple mathematical modeling for this mechanical systems and then electrical systems and hydraulics and pneumatic systems.
right,
So we use generally the basic of the Newton's second law and all these things.
right,
Simple
right.
things we have used to do this.
Yes, yes, yes.
As far as electrical systems are concerned, then the this Kirchhoff voltage and current laws and all these things that will, and then
Yes,
we
yes.
put some analogies between this, and according to that we tell the students basically
Right, right.
how to model these systems basically. So
Yes, yes.
there we just use the second law of the Newton's second law basically as
Right,
far as
right.
this concerns these are concerned over there, and we just put this the analogies between this what you have just told you tell me that regarding the resistance capacitance is analogous to the different elements in the mechanical system as a spring basically capacitance is analogous to the spring itself only.
Right,
So we try to make this to understand the concepts by these analogies over there because
right,
some students understand electrical systems very good, so we correlate it with this mechanical systems and then put it in the uh, using the basic laws and all these things try to make a model, and from that we try to understand then the transfer function and all these things, transfer function modeling and all these things,
right, right.
and to find out the transfer function of the systems, basic systems, and then responses. And we try to use this some of the open source basically, sir. What the IIT Powai basically they have this open source is there for the Scilab something like that.
Yes, yes, yes.
So I used to have these XCOS and all these things. So
Okay,
we do this is modeling on this XCOS
okay.
and try to simulate the system on the XCOS and try to show it first order, second order systems responses of this.
I see.
So we try
So,
to do these things, sir, at our level basically.
I see, I see. So, what was the name of
So
the
very
software?
simple thing we do, sir. That the gear ratio and all these things, the complicated models are the because students are not able to connect so many things over there. So we do simple things, not that much complicated things over there.
Right.
The gear ratio and all these things they are not able to digest in terms of this transfer function and all these things, sir.
Okay. Right, right. So, what was the name of the software that you mentioned?
I use this Scilab Xcos, sir. Xcos.
Xcos. So, it's like within Scilab. So, it's a lab. Is it
Within
an?
Scilab, there is a tool basically which is called Xcos.
Okay, okay.
So this is open source basically. That's why it's freely
Right.
available. So you can download it. Like any student can do it, sir. So that I do it in the Xcos basically. MATLAB
Okay.
is a commercial level
Right,
basically.
right.
So we
Yeah.
try to make it in Xcos, Scilab Xcos basically.
Okay, okay. Yeah, I actually was not aware about this particular tool. So, yeah. So, I think maybe I'll also explore.
So see the bond graph basically somewhat not difficult I will say, but it is intermediate between something. So there is a flow of energies and all these things. Something is missing over there. I the concept what is there. What I feel is that by using a simple Newton second law and all these things, it's easy to students will understand this. But the bond graph basically you have to go with the very basic again for every element you have to tell everything over there,
Yes,
and
yes,
then
yes.
just what you're told regarding the uh, what I can say the two to three basic elements are there, and then additional elements are there, and there is a there is a transform or something which is there,
Transformer.
which is something which is I can correlate it to the transfer function.
Yeah.
So some sort of analogies, if it is there, then it's easy to understand, sir. That
Yeah,
is
yeah.
the
Right, right. Yes, yes.
so the bound
So,
graph basically. I don't know exactly. It will take some time for me to understand this thing.
yeah.
But initially, I understand the basic elements of this and all these things. But by constructing it, I have got some difficulties. The arrows basically how it goes. Is it following the what I can say the energy flow or something like that? I don't understand that. How they are making this. Is it depend on the loops or something like that? With current flow in the loop and something like that over there.
Yeah, it is basically the direction, like with whatever arrow that we create, that is
Uh-huh.
representing the direction of power flow. So,
Uh-huh.
like if
Uh-huh.
let us say there is a series like circuit of let us say RLC circuit,
Uh-huh.
let us say like there
Uh-huh.
is some voltage source, for example, like let me just draw here. So then, uh, so like if there is some voltage source, then some inductor and then capacitor and all like so these let us say these things are connected in series, so then there is only one common current that is flowing here. So in
Mhm.
terms of bond graph, what we represent, so let us say this voltage source, so what we represent this as basically source of effort which has like voltage, and then we just draw one line which is representing the power flow now, and then we basically now, because there is one common current that is flowing across all three components, so then we represent this as one junction, and from this junction power is flowing to all these three elements. So let us say one is, let us say, inductor, like resistance, inductors and capacitor. So these arrows are basically just showing that the power is flowing from, like, from the source up to these, like, resistance, inductance and capacitance. So resistance will dissipate energy,
Yes.
inductor and capacitor will store energy, store or
Mm-hmm.
release depending on whatever
Mm-hmm.
like the situation is. But
Mm-hmm.
broadly this is just representing the power flow direction.
Okay. Okay. Okay.
And
Okay.
now in terms of causality, so this is like one junction. Now if the thing was in, like, if we have like a current source, now it's like same kind of circuit, but let us say if this is a current source, so yeah, so this, if this is current source, and then we have, let us say, all these three components now in parallel, let us say inductance, capacitance and resistance, all these things. So let us say if we have them in parallel, so then we represent it as, so this is source flow, so then we call it as source of flow, SF. So where current I is being provided, and then we represent it as a zero junction now, because the voltage difference across all the components is same, but the current is being distributed across these three things. So the flow is being distributed. So then there will be again same kind of like three arrows in the bond
Mm-hmm.
graph. Uh, so one will be basically the resistance, capacitance and inductance. But now we are representing this whole thing as a zero junction, because so essentially power itself is flowing. So either voltage is same and current is being distributed, or current is the same, current is flowing, but the potential drop is different, and then that, so the arrangement may be different, but essentially it's just the flow of power. So the arrows just indicate the flow of power. The bond graph will be similar. The only thing is what is the quantity that is like being distributed. So whether it is current, so the flow, whether the flow is being distributed, or whether the effort is being distributed, so like that way. So
Mm-hmm.
like you can like probably visualize it in terms of that way.
Okay.
So yeah, so I hope that helps.
Okay. Okay.
Yeah, so basically my plan for today's session was to basically cover some problems
Mm-hmm.
on this particular week's content, which is uh, so the dynamic response of first order and second order systems, the
Mm-hmm.
performance measures for the second order systems, like the measures what we generally know, like rise time, settling
Mm-hmm.
time, then peak
Mm-hmm.
time, all these quantities, how they are defined, and we will
Mm-hmm.
basically look at some problems where we'll calculate these things, and then
Mm-hmm.
like problems where we use the concept of Laplace transform to derive the transfer function
Mm-hmm.
of first order and second order systems. So this week's content was related to that. So for today's session, I have basically planned to cover problems related to that.
Okay.
So yeah. So shall we start with that, or do you have any other questions or comments, sir?
No, no, no.
On
You can start with that. No issue.
Okay, sir. Yeah. So like yeah. So sir, like which institute, sir, are you teaching?
It is located in Pune.
Pune only. Okay.
Uh, near RTO Pune, basically, near Mangalwarpet metro station.
I see.
Okay.
Okay,
Uh,
okay.
it is All India Sri Shivaji Memorial Society's
I see.
college
Okay,
of
okay.
engineering.
Yeah, yeah.
Uh-huh.
Myself, I am also basically belonging to Pune itself.
Okay.
Yeah,
From
yeah.
which college you are passed out?
Yeah, I did my bachelor's from BITS Pilani Goa campus,
Okay.
and then I did my MTech from IIT Bombay, and so I worked for industry for around 4 years, and then I've joined back for PhD.
Okay.
So
Okay.
yeah, so it's like
So your basic degree is in mechanical
mechanical,
or it is
yeah,
mechanical?
mechanical, yeah.
Okay. Okay.
Yeah, so I know
Okay.
like AISSMS, I know, yeah,
Okay. Okay.
right, fine.
You can proceed, sir. No, no issue.
Yeah. So yeah, so I'll just be back in 1 minute. So yeah, so I just need to get some water for myself. So like I'll just come in a
Okay.
minute. Yeah,
No issue. No issue.
yeah.
Gayatri?
Hello, hello. Yeah, yeah. So like before we start, actually, I just wanted to mention one more point about bond graph, which was basically causality. So so I'll just quickly mention that, and then we can go proceed. So like for causality in the bond graph, so so we indicate the causality bar on the side of on the like the side where we calculate the flow. So so for the source of effort, so we generally like the effort for a known effort, we are calculating what will be the resulting flow. So that's why we indicate the causality bar here. And for inductor and capacitors, like we have the preferred causality. So then for inductor, so we have the preferred causality that the flow flow is being calculated on one side, and like the effort. So so for resistance and capacitance, so there is like a convention of like or preferred causality for showing the the bars. of the causality, whereas for resistance, like we have the free causality, and depending on the type of junction, and then so for the rules, depending on the rules of that, like the junction and all, so we decide the causality, where to put the causality. So for capacitance, we know that the current across the capacitance is basically C into dV by dt. So where V is the voltage across the capacitor. So the voltage but we like we while defining the causality, we prefer the integral causality. So what we say that is that voltage across the capacitor is 1 by C into integration of current I dt. So we represent it preferably in the integration form. So that's why like our um, causality bar for the capacitance, so it would be on the this side, like, whereas in inductance, so the voltage drop across the inductors is basically uh, L L into di by dt, where L is the inductance and I is the current. But now, as I said, like we represent it in terms of integral causality. Basically the voltage across inductor is L di by dt. So therefore we represent the current as 1 by L integral I dt. So integral into the voltage dt. So that's why, we are calculating the flow from the using the basically the effort. So that's why like the causality will be on the this side, like. And then for one junction, because of the rules, so we will be assigning the causality on this side, because one junction should have, like, let us say, for where there are n bonds, so it should have n minus 1 causality bars at the one junction. Now on the other hand, so for the zero junction, we will assign the causality bar on this side, because the flow is known. And so as we know, for the capacitance, now here these are the preferred causality bars. And then it should have only, so if there are n bonds, so then there should be only one causality bar for the across the zero junction. So therefore the causality bar should be here for the resistance. So these are like the general rules of the bond graph, so which we can use for construction. So yeah, so I hope that helps somewhat. So shall we start with the problems?
Okay.
So yeah, so I have initially some simple multiple choice questions. So yeah, I was actually expecting more students to join this particular session, so that you know we can interactively solve the problems together. So yeah, so basically here we have been given like the transfer function of a first order system under unit step input is this one. So we have to calculate the time at which the response can reach 63.2% of its total change. So which is basically the time constant. So generally the general form of the transfer function for the first order system is so so where tau is the time constant. So where g is the gain and tau is the time constant. So here we have been given 1 upon 5 s plus 1. So therefore the time constant tau here will be 5 seconds. So the correct answer to this question will be 5. So these are the like general simple type of problems which you would encounter in the assignment weekly assignments for this course. So now applying the same logic now, so what would be the transfer function for this particular uh, transfer function now? So it would be 7 by 16 into, so now if we compare this with the general form, so we will get basically the gain value is 7 by 16 and the time constant will be 9 by 16 seconds, which is so 0.5625 seconds. Now the next question in which we have basically a second order system. Uh, so we have been given the differential equation for that. So so we have to find out the order, damping ratio, and the nature of the system. So as we know already that because the differential equation is second order, so the order of the system is second. So then we have to convert this differential equation to into basically we should divide the whole equation by 5 so that it becomes convenient for us to find out what will be the damping ratio. uh, so then so I'll write it as, so basically x double dot plus 5x plus 20 is 0. So if we divide the whole equation by 5, so then we know that uh, the undamped natural frequency is 20 and 2 zeta omega n is 5. So basically So therefore zeta, which is the damping ratio, so that will be 5 by 2 omega n, which is 5 upon 2 into root 20, so which is 5 by 2 into 2 root 5, so which is basically root 5 by 4. So the value of this comes out to be, so what will the value of this be? So it comes out to be around 0.559.
6.
And so therefore, because the damping ratio is less than 1, it is under damped, and its value is like 0.559, which is approximately 0.56. And yeah, and it is a second order system, so the correct option for this is option D.
You're comparing this equation directly with the standard model, na? You directly written omega n square is equal to 20, 2 zeta omega n is equal to 5.
Yeah.
So you're considering you're directly writing means you're taking a standard form of this second order system, idealized form, something like that. Na?
Yeah, so that's like the simple, usually the,
It
you can
is
say the underdamped case. So now if the, now luckily it came out to be like that. Yeah, so otherwise we would have to go by, let us say, the other standard approach would be to actually calculate, like let us say, the roots of this equation. So here, so we have to check like the, let us say, this quadratic equation x double dot plus 5x plus 20 to actually calculate the roots of this, so which we can check that it will actually turn out to be imaginary. So based on the nature of that, so we can yeah, so ideally that approach would be, yeah, better. But yeah, so we can also like try out this whether like comparing these constants, it actually came out to be under damped. Um, but yes, so ideally the approach would be to actually find out the roots of this quadratic equation to check
okay.
whether they are real or
Mm-hmm.
equal or imaginary.
Mm-hmm.
Yeah, so that would be, so what we will do is, so in that case, yeah, so I have no space left here, but basically to check whether the
No, no. Generally, see, there is a standard form is nothing but s square plus 2 zeta omega n s plus omega n square.
right,
We
right.
write to the transfer function for this type of a system. Basically, you have made the second order, the coefficient of the second order, what I can say, the x, you have made it 1 over there, no? X double dot. So you're just dividing 5 means you're making
So
it 1 over
your
there.
voice is not
So
audible, so okay.
is it audible now? So x double dot plus 5x plus 20,
Yeah,
the transfer function comes out of the s square plus 5 2 zeta omega n s plus omega n square like this, no?
yeah, yeah, exactly.
That's why written is omega n square is equal to 20 directly. 2 zeta omega n is equal to 5.
Yes, yes, yes,
Yes, no?
yes, yes, yes. You're right. Yes,
Okay.
exactly.
Got it, got it. Okay.
So yeah, Yeah, so that would be the standard form if the system was underdamped. Now, whether the system is actually underdamped or not, so then for that, like, so for that, like, we can check whether the coefficients, like, in case of the quadratic equation, we have to check whether the quantity under the root, so root, like ax square plus bx plus c is equal to 0. So for that, b square minus 4ac has to be positive. So so here 5 square minus 4 into 20, it will be basically something negative. So therefore
Mm.
the roots will be imaginary.
Yes, yes, yes.
So or
And
complex roots, in other words, actually the roots will be
complex
complex
conjugate
numbers.
roots. Yes, yes, yes. Got
Yeah,
it,
so
got it.
because it has complex roots, so then we can immediately say that it will be underdamped.
Okay.
And then from the roots, we can compare like those coefficients as we did to get
Hmm.
like the roots. We can write it in that standard form. So the
Okay.
coefficients will actually come out to be that omega n square is 20 and then 2 zeta omega n is 5. So like that.
Okay. Okay. Okay.
Yeah. Now in this problem we have been given a torsional system with the torsional stiffness. The mass moment of inertia is given. Yeah, I think the torsional stiffness value I think seems to be missing. But yeah, so anyway, so like I think because of some issue, this torsional stiffness value I think got missed somewhere. But yeah, so the model for that system will be basically that the net torque. So where I is, let us say, the moment of inertia, and theta is the angular displacement. So rate of change of angular displacement. Uh, so I theta double dot, or the angular acceleration, is basically given by k theta. So here k is the torsional stiffness. So we can rearrange the equation to write that. So the natural frequency of torsional vibration would be basically ratio of the um, torsional stiffness to the moment of inertia. So from that we can find out the natural frequency. So in radians per second it will be root k by I, and in hertz, so let us write it as Fn. So it will be basically natural frequency by 2 pi. So in hertz.
The stiffness value has been not given in the problem basically. No?
Yeah, I think that got missed
You
somewhere.
miss out
So yeah, I
something
think
corner.
maybe I
Huh?
missed to like write it somewhere. I think so. Yeah, if we like consider it as some value, so yeah. So anyway, it's not like that. Numerical value is not really important here. So we can just leave it.
Okay. Understood.
Essentially, what we have to do is this. The model is this. Now, yeah. So in the next question. So it is asked like for a second order spring mass damper system, the fastest possible non-oscillatory response is obtained for what value of the damping ratio? So what do you think would be the answer to this? So let us try to sketch the typical type of response. So let us say we are trying to sketch the like the response for an undamped system, let us say. So if there is no damping, then the response will be, let us say, something like this. So there will be continuous oscillations.
As
And
equal to zero on dam system. No?
yeah, so this is like undamped case where zeta is zero. So no
Because you get
damping.
that dam system over there. Zeta is equal to 1. It's critically damp, I think so.
Yes, 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 you're right.
Less than 1 is under dam system.
Yeah, less
And
than
more
one will
than
be
1 is
under
over
damp.
dam system, basically.
Yeah, so if it
So the
is,
fastest response will be the critically damping mode, equal to 1, I will say.
yes, yes, you're
Is
right.
it correct?
You're right, sir. Yes. So if it is under damped, it will oscillate
Yeah.
and takes basically takes some time to settle down to the steady state value. So the response will decay, but it will take some time to settle down. Now in case of let us say critically damped system, so there will be no oscillation. So so it will basically just without oscillating, it will just go to the steady state value. So yeah, so that's like critically damped case. So where the so for damping greater than 1, and this is like this is like for some damping value which is less than 1. So equal to 1 will be the case where we will settle down to our steady state value at the fastest rate. Now we have been given some statements here. Which one of them is true is what we have to find out. So, so the first statement says that the maximum percentage of overshoot directly indicates the relative stability of the system. So, which is actually true. So, the uh, overshoot actually uh, measures like how far the response of the system overshoots or undershoots the uh, steady state value. And if the overshoot is more, so then it will take more time to settle down. So yeah, so it indicates the relative stability of the system. And decrement, second statement is decrement is the ratio of first overshoot to second overshoot. So do you think that is correct? Is that true?
Decrement basically under damp. Basically, decrement
Yeah, so
basically
decrement is defined for the underdamped system, and
yes,
it
no.
is like for the underdamped system, it's the ratio of amplitude,
Oh,
uh, like so if let us say so x1 is, let us say, the amplitude of this peak, x2 this one, and x3. So the decrement
but
is defined as x2 over x1 or x3 over x2.
yes, yes,
So it's
correct.
basically the ratio of second overshoot to the first overshoot, because it's a decrement, so it's
Hmm.
so that's why this statement is not correct. As the damping ratio increases, the percentage of overshoot decreases. So that is also true. So as we go on, as we just saw here in the previous example, so the overshoot from the steady state value will decrease as we go on increasing the damping ratio, and for overdamped, like there will be no overshoot at all.
Yes.
And yeah, so that is true. And then the fourth statement, that number of oscillations are independent of damping ratio. So that will not be correct, because the number of oscillations itself actually depends on the damping ratio directly. So more the damping, lesser the number of oscillations will be. So the correct answer to this question is option B,
Point three.
1 and 3. Yeah. So in this next question, so we have been given a system differential equation. So here we have been given that the coefficients are partially given. So we have to find out the value of the coefficient C to have the damping ratio of 0.5. So so now we can again use that same approach which we used in the previous type of example, which was basically, so we write the equation in this form. So x double dot plus 2 zeta omega n x dot plus omega n square x is equal to, sorry, sorry. Uh, so now if we compare the coefficients here, so we can see that C is basically 2 zeta omega n, and omega n square is 10, and we have been given that zeta itself is 0.5. So then C will be 2 into 0.5 0.5 into omega n, which is root 10, which is, 3.162. So shall we proceed with the next question, sir? So now in this question now, we have been given the differential equation and we have to calculate the damping ratio, rise time and peak time. So, so now, so we have to convert this differential equation, like the coefficients are given, but we need to convert them into the proper standard form of x double dot plus 2 zeta omega n x dot plus omega n square x is whatever some by or whatever. So here it will be basically, so if we divide the whole equation by 10, it will become x double dot plus 0.5 x dot so 0.1 is equal to y. So then, so we will get, so basically comparing the coefficients, we will get omega n square is 0.1 and 2 zeta omega n is 0.5. So what is the value of zeta here? Then zeta will be 0.5 divided by 2 into root of 0.1. Which comes out to be
Consistent. 0.79. 0.79 something.
Yeah, it comes up to be
7.69
0.79.
something. Damping ratio. Less time.
So then the rise time is the uh, time required to complete basically pi by 2 radians. So it will be basically pi by 2 into the damped natural frequency. So the damped natural frequency will be omega n into root of 1 minus zeta square. So which is so I think it comes out to be point some 0.0613 for the damped natural frequency omega d. So this is the rise time Tr, which is pi by 2 omega d. So the rise time it comes out to be I think around 2.562 seconds for the rise time, and for the peak time, so peak time is which is I think there is So I think this should be 25.62 and this will be 51.25 approximately. So I think you will get like this. So for rise time and peak time. So you can check the calculations, but I think the method is basically this. So shall we proceed with the next problem? So the next question is about stability. Uh, so we have been given two transfer functions. So basically 1 upon s plus 10 and 1 upon s minus 10. So which one of them are like stable or unstable? So we have to state that. So now how do we answer this question?
Finding the poles now.
Right. So we have been
Numeric
given that.
denominator. Yeah. So that is the poles of the system also. This one.
Right. So for this, so here, so for this transfer function here, so in one case the pole value is plus 10 and in one case it is minus 10. So in the case where the pole is minus 10, so 1 upon s plus 10, so for example, so here the Laplace inverse for this will be e to the power minus 10. Is that correct? So is the Laplace inverse correct here?
Plus.
Yeah, so basically the Laplace inverse of the transfer function 1 upon s plus a is e to the power minus at. So, so yeah, so that's correct. So, and in the other case, 1 upon s minus 10, the function will be e to the power 10t. Now, if we plot the graph of these functions, so let us say this is f1, this is f2. So for the function f1, the
In
graph would be
exponential decaying.
like
It's
this.
exponentially increasing.
So this is for f1 and for f2 it
Decaying. Second
would
one
be exponentially
is
increasing. So,
okay. The answer is D.
so basically f1 would be a stable function, and f2 would be become basically unstable. So as time increases, the amplitude keeps growing. So therefore, so the first system is stable and the second system is unstable. So the correct answer to this question is option C. Now in the next question, so we have been given some the basic types of inputs here. So it's basically just a simple question where we have to find out what is the type of input for each of them.
Option is B.
So A is basically a step input, B is an impulse, and C is a ramp input. So the correct option, so basically, so if we write down, so this is step, so this is impulse, so this is impulse, this is ramp. So the correct option will be A is step, B is impulse, and C is ramp. So correct option will be D. Is that okay? So now in the next question, we have been again given a differential equation for an armature controlled DC motor. So armature controlled meaning that, so basically in a DC motor we have two types of like windings. So armature, or basically on the rotor. So if you have windings on the rotor and windings for to generate the magnetic field on the stator, let us say. So those are called field windings, and these on the rotor are called armature windings. So for an armature controlled DC motor, we keep the field current constant. So the magnetic field becomes constant, and then we vary the armature voltage to control the speed of the DC motor. So this is the differential equation which represents that. So we get this differential equation uh, for the case where if we neglect the inductance of the armature. So then it becomes a first order system in that case. So now what will be the time constant of this uh,
You can take the Laplace of both the side.
right? So we can take the Laplace transform for both the sides. So then what we will get is So the transfer function will be which is basically 1 by a3 upon now if we compare this with the form gain upon tau s plus 1. So in this case tau will be the time constant. So if we compare the coefficients, so the gain will be 1 by k3 g. So g will be 1 by k3 and the time constant tau will become
One R K3 by K4.
now we can also solve like this actually solve the differential equation further like using the Laplace inverse and all like this for this particular thing. So that can also be done in this case. So what will be the Laplace inverse in this case?
Okay.
Yeah, so we can also solve using the Laplace inverse like so to find the time constant of this like transfer function, so we can just simply uh, like subject this to a step input. So then it will become so from for and take the Laplace inverse of that. So then from that we can get the step response of that system. So so basically what I mean to say is so the so so subject it to a step input, so 1 by s and take the Laplace inverse. So from that we can again get solve for the we get the actual response to step input, and from that step input response, so we can find out the time constant from that also. But yeah, so we can also like just simply compare the coefficient because this is the usual form in which the transfer function appears to be. So then so from that the coefficient we can just guess what will be the time constant from that. So is that okay?
Okay. Okay.
Yeah. Next again we have like a just like a simple spring mass damper system where we have been given the mass, stiffness and the damping coefficient. So we have to find out the value of the frequency of damped oscillations. So we have been given that mass is 12.5, stiffness K is 1000 and damping is 15. So
Square root k by
so so omega n will be
1000 divided by 15.
square root of 20.
6.66.
So it will have come out to be around 8.94 something.
8.164. 64. 8.165. 8.17. Damp oscillation frequency. Omega square root of 1 minus theta square. 8.164. 6.66.
So the value of the critical damping factor
Square root
is
km.
2 root km. So then the damping ratio becomes 15 by this 223.61, which is around 0.0671. So the damped natural frequency will be, so this is basically equal to just zeta. So it is omega d is omega n into root of 1 minus zeta square, which will be
Six,
so this will be in radians per second, and this divided by 2 pi comes out to be around 1.42 hertz. So is that correct? So is that, are you getting the same answer, sir?
yes, yes. 0.449.
Okay.
Okay.
So then we come to our next question. So an accelerometer has an undamped uh, frequency of 100 hertz and it has a damping factor of 0.6. So we have to find out what will be the maximum percentage overshoot and the rise time when it is subjected to a sudden change in acceleration. So we have been given that omega n is 100 hertz.
2 pi,
So
2 pi
2
f
pi into 100,
multiplied by 2 pi comes to radians per second.
so in radians per second.
Hmm.
And zeta is 0.6.
Damping factor zeta is 0.6 under ram system. Yes. What will be the maximum percentage overshoot and rest time?
So rise time is basically just
Pi by omega point omega d.
and
Omega d is 1 minus zeta square. Square root 1 minus zeta square. Omega into square root 1 minus zeta square. 0.6. 0.6. 26. 26. 0.64. 0.8. 0.8 into 0.8 into
0.8.
502.
So rise time will be 2 pi into 80 or 160 pi basically. So pi by 2,
165. 160. Just 320. 1 upon 320. 1 upon 320.
yeah. So it will be 1 by 320 and percentage overshoot. So for that we already have the formula of so
It
for
is power of square root of something. 1 minus.
so the maximum percentage overshoot is given by e to the power minus pi zeta into 1 to the into 100. So zeta is zero point 0.6 and root of 1 minus zero point 0.6 square so is zero point 0.8. So it's basically 3 by 4 minus 3 pi by 4 into 100.
Negative. E to the power of bracket minus point.
So it comes out to be something around 9.478%. Is that correct? So are you getting the same answer, sir?
0.94. Yes, correct. 9478.
Yeah.
Yes. E to the power of minus 0.14. Got this. Then 0.0947. Got it.
Yeah. So then, shall we move to the next question?
63.2.
Yeah.
63.2.
Yeah. So it is 63.2% of its steady state
Steady state
value.
value.
So it's like basically if for the first order system, so if the response is something like this, so for t equal to tau, so x by x naught is 1 minus e to the power minus 1, so which is 0.632.
Mm. 360. Okay, got it.
Yeah. Now we have the next question. So for the system where the transfer function is 1 upon s square plus 6s plus 9, when it is subjected to a unit step input, so what would be the output as a function of time? So for that we have to find out what will be the poles of the transfer
Okay,
function.
equal to 3. 3.
So what will be the poles of this? So the roots of this
By
equation will
n
be
is equal to 2 pi zeta equal to 6 minus 2 zeta zeta is equal to critically damped system.
right.
Critically damped system.
Yeah. So basically omega n is 3,
Critically damped system.
right?
Critically dense system.
Yes, yes, yes.
Oh,
It's
critical
not
dense
equal to
system.
1, so that's why we will get critically
Critical
dense.
dense system. Yes.
Yeah. So the poles are basically, so the transfer function is basically 1 upon s plus 3 whole square. So in the next question, we have to find out the transfer function. So here, so we have been given this differential equation.
dy by dt has to be taken. A minus a dy by dt has to be taken.
So we can just take the Laplace transform for the differential equation. So, so now for taking the Laplace transform, one important assumption is that we assume that the initial conditions are all zero. So, so now we have to collect the terms of y. So, so the input is x of s here, and the output is y. So basically, y of s upon x of s is something that we have to find.
Yes, square plus. Mm, mm, got it.
So this would be the Laplace transform.
Mm,
So we can further simplify it to so the transfer function will be y of s upon x of s will be.
it's not visible. Hello.
Hello. Yes.
The screen is not visible.
Screen is not visible.
Okay. Yes, yes. Now it is now visible.
Okay.
Okay.
I can see the screen for
Yes, yes,
myself.
yes. I can.
Are
I
you
can
able
see
to
it
see?
now. Yes, yes. I can see it now.
So the transfer function can be written like this. So it has one pole at s equal to 0 and another negative pole. So that's how we can like use simple Laplace transform for deriving the transfer function. So is that okay, sir?
Hello. Yes.
Yeah. So shall we proceed with the next question? So shall we proceed with the next question? Yeah. So in the next question, we have been given this problem. So where the car is going over the road. So we have basically assuming a lumped parameter kind of a model of the car. So the car body is like modeled as one single lumped mass, and like the stiffness of the suspension is modeled as the spring, and damper, which represents the the damping of the stiffness. So now what is happening here is that the car is going over the road and the tires are in contact with the road. So the tires are basically being because of being contact with the road, so they are providing the excitation to the car body through the displacement of the tires. So basically the up and down motion. So as the tires are going over the road, so they will undergo up and down motion. So if we draw a more simplified representation of this, so the this wheel, so let us say this is the wheel of the car and it is undergoing up and down motion because of its motion of going over the road. So this is, let us say, mass m, this stiffness and damping. So let us assume that the vertical displacement of the tires, we will assume it as y of t, and this vertical displacement of this mass m of the car body, we will assume it as x of t. Now to derive the transfer function of the basically the amount of displacement of the car body relative to the
क्या बोलूँ मैं
displacement
किधर
up
बस
and down
गियर
movement
होगा
of
पर
the wheels. So for that we can apply basically Newton's second law. So for that, so we have to first draw the free body diagram. So, so to draw the free body diagram, we will assume one thing, that this deflection x of t is measured, and y of t, both of the, like, let us say they are measured with respect to the equilibrium position. So the static effect of the static deflection, uh, because of the weight of the mass, is taken care of. So then we will not need to consider that force in our free body diagram. So the only dynamic force acting will be the spring force and the damping force. So let us assume that for at the particular instant the spring is in tension and the mass is, let us say, moving upwards. So therefore the so what will be the expression for the spring force? So let us assume that for the particular instant that we are talking about, so let us say x is greater than y, so that's why the spring is in tension. So spring is also subjected to the same tension, and the damper is also being subjected to that same force. So the spring force will be K into, and the damper force will be x dot minus y dot. So these are the only two main forces acting on the mass. So now we can write down the Newton's second law for this mass. So basically m into x double dot is equal to the sum of net forces, and because it is moving vertically upwards, so and the forces are acting downwards, so we will get the equation like this: c into x dot minus y dot. So basically mx double dot plus cx dot plus kx is equal to, so this is our differential equation now. So now what we will have to do to get the transfer function now? So we have to basically just take the Laplace transform of both the sides. So then we will get So now assuming zero initial conditions. So this is the Laplace transform of the left hand side, and so so now the transfer function of the displacement of the car body in terms of the excitation with respect to the excitation or displacement excitation from the road will be so this will be the transfer function for the so basically this is the transfer function between the displacement of the car body and the excitation provided by the road because of the up and down motion of the tires. So this was these were some problems which are similar to the assignments that we have discussed today. So I still have many other problems in this sheet. So I think you can try those on your own, and we can discuss them in our next session. So you can use like practice these problems, and I hope this session in general was helpful for you to understand the course content and solve the assignment problems. So yeah, so because we are coming to the end of today's session, so that's all that I had from my side for today. So if you have any questions or comments, so you can say then, or otherwise we can end the session for today. So sir, do you have any questions or comments? Yeah, so yeah, thank you, sir, for joining the session, and I hope this session was helpful for you to get some idea of this like the general course content, and I hope it helped you like to practice the problems in the assignments. So I also have some other examples, so which we can, if you have any difficulty, we can discuss them later. So yeah, so I think we can end today's session over here if there are no further questions. So shall we end the session, or are there any questions, sir?
No, thank you, sir.
Yeah, okay. Sure. So thank you, sir. So yeah,
Thank you very much.
yeah, thank
It's a
you.
good session.
Yeah, thank you very much, sir. Thank you. And yeah, so do let me know if you have any questions in the next session. Okay, sir. Thank you very much. Good night.